Thanks for coming. This talk is about the functional database. Mike, it's there we go. It's green. This talk is not specifically about Datomic, but Datomic is the example I'm going to use. You could substitute any functional database you like. So the first question I have is, how many people here do functional programming? How many people do it in a functional language? How many people do it in a non-functional language? All right. How many people are skeptical of functional programming? It's okay, all right. So why do we do it? Do we do it to stop us from accidentally doing I/O during computation? How many people have written some math library and accidentally talked to the internet while they were doing it? And they need monads to keep them from doing that. Nobody, that's right. That is not why we do functional programming, I don't think. One way to think about this and think about functional programming and what our programs do is to try to distinguish the parts of our programs that are computationally oriented and the parts of our programs that are like machine oriented. They're like little machines. And I think that when you think about languages and you think about programming, you can think about languages being on a spectrum, right? There's assembly language, which is sort of like talking directly to the machine, and it feels very much like make the machine do stuff. And then there's C, which is also still very squarely in the category of make the machine do this, then make the machine do that, then access this part of the machine's memory and do whatever. And some of those programming languages are like that because the people using them are building things that are substantially like machines, like operating system kernels and things like that. But that's really hard to do, and it's extremely hard to do well. And so when we consider higher level languages, we measure them sort of by the extent to which they keep us from having to think about things in terms of make the computer do X. Because just because the computer is a machine, and it is one, it doesn't mean that our programs should consist of machines, right? Where a machine is something stateful that goes from this to that, and it's doing this, and then it's doing that, and then doing another thing. And there's a sense in which objects are like little machines. And I mean that in the most pejorative way possible, right? That's what they are. And it ends up that that's really difficult to think about, right? And especially when you think about combining different machines, things that are moving around. It's very difficult to reason about. So the whole benefit package, I think, the immediate benefit package from functional programming is it allows us to choose something other than machines as the model we use in our head for thinking about what's happening in our program. It gives us an alternative to building computations directly out of machines. And the recipe for functional programming is basically combining values and functions. And I'm not going to dive off into a talk about values, except to say that when I say value, I do mean something immutable. How many people were in Eric's talk earlier? Right, so immutable means not in the I/O monad. Okay, so just another way to say the same stuff. It's something that can't change. And everything that he said and all the premises and all the math that he showed you doesn't work if any of the arguments to any of the functions are mutable in the way that we consider it to be true. So it ends up that immutability is quite important. But when you combine immutable values and functions, which take more than one, a value or more than one value and produce another value and always produce the same value as a result of given the same arguments, you end up with something that's more like math. And that's very much easier to reason about than reasoning about machines that are moving around in different states. There's a sense in which mathematics doesn't have any notion of time and or state. That doesn't mean that there aren't machines in our programs. At the bottom of even the coolest functional programming constructs are little machines, right? You can't implement laziness in a functional language without a little machine that does caching for you. But that doesn't mean that's the abstraction or that's the level at which we want to be working most of the time, because we don't. It's far too complex. We all like doing that, right? Everybody who's implemented a really cool data structure or a cache or a queue or something like that has written a little machine. But we want to isolate that work and the amount of time we spend doing that kind of work to the corners of our applications where that's necessary, which is very, very small corners. So it's more like mathematics. And the bottom line is it facilitates reasoning. I'm not talking about any kind of formalism here except thinking. Right? It lets us think about our programs, and the easier our programs are to think about, the better our chances are of getting them right. So if we're going to have something we're going to call a functional database, I think it has to meet a couple of requirements. The first thing is it has to provide a database as a value. Right? And I'm going to go even further than immutability in a minute and talk about persistent data structures, but it really needs to provide the database as a persistent data structure, something that's immutable, because only then can you get the second part of the recipe for functional programming, which is you should be able to write functions that take a database or databases as arguments, and maybe even return a database as a return value. Right? If you can do these things, you have a functional database. In addition, if it's going to be called a database, it has to be able to do the other database stuff, right? It has to be durable. And I'm going to distinguish that from persistent. Persistence is a sort of a characteristic of data structures, immutable data structures in memory, and durability is, it's been put somewhere so that if every machine was turned off, we turn them all back on, we could find it again. Consistency is another thing we seek in databases we don't always get. Leverage is an important property of a database, right? A database isn't just a bag into which you've dumped stuff, and every time you want to do something, you have to go through everything in the bag. Right? If you're doing that, then you're not getting any leverage. It's just a pile of bits. So databases have to give us some leverage. And the other traditional characteristic of a database, although it's not always present, something we desire most often from databases, is that they're shared. And this is where it gets tricky, right? Because we have lots of constructs for dealing with immutability and state management in memory, in process, in a particular programming language. But the nasty thing about a database is it's outside of all that, and there's more than one process, possibly in more than one language, and definitely with more than one idea of what's going on, sharing this thing. So far, databases have been treated like giant shared global variables, and all the values we seek in choosing functional programming are not present for databases normally. I'm going to make the claim that a functional database value, right, so the value that you get when you look at a functional database, should be an accretive thing. That means that it should be something that grows as more information enters your system, that it accumulates everything that's happened. And I've given other talks about why that is essential for an information model. I also think it's sort of an essential implementation detail of doing this, right? Because your alternative is something like snapshots, and then you have the whole question of how do I find a snapshot corresponding to a particular point in time, and can I ever do anything that crosses time? So I'm going to be showing you some things today that are benefits of being accretive in addition to being benefits of being functional. I think they go together. In any case, there's no doubt if you're going to have a value of a database, it has to be immutable, or else you can't do any functional things with it. So far I've been saying the word database over and over again, and I think there are two notions of a database that we normally don't disentangle that we now have to start doing. And if you've seen my talks about objects, this is the same kind of thing. Right? We need to separate out the identity of an object from the state it takes on at any point in time. And when we do that, we can start writing functions of this state, and we don't get into trouble trying to manipulate a machine directly. So there's this notion of a database system. Right? There's something that's going to go and facilitate multiple processes interacting with some shared data set and being able to get values out of it and grow it by putting more information into it. And that is actually going to be a machine. That's going to be some process that works a lot like a machine. Right? There's a conveyor belt, stuff gets taken into it, it bakes some new cakes, it gives out new cakes to everybody else. And that's where the identity part of the system is going to live. Right? There's some database, it's called our customer database. Well, we know the idea of our customer database persists through time, but the values our customer database takes on change over time, right? We get new states of the database. Usually there's more and more customers in it. It could be the case that when we lose a customer, we erase them, but more and more we're finding that businesses value information models. They don't want to forget things that they knew because there's a lot of value in doing time-based analysis of what happened. Does this person change their email address all the time or move all the time? Well, if every time they give you a new email address or a new address, you erase their old one, you'll have no idea. Does your supplier change their prices all the time? I don't know. I just take the price and I overwrite the old price. You can't learn. As people, we use time-based decision-making all the time, yet we build systems that are supposed to be information systems that forget what happened. So we want to accumulate stuff inside this thing, and there's going to be something that coordinates that. And then this machine is going to deliver to us when we look to perceive the database, values. And these database values are the things we're going to use to do computation. Disentangling this is sort of the essential job of building a database that's going to be more functional. This talk is primarily going to be about the second part. But let's look at what this looks like. So this is the traditional thing, where I'm going to say the entirety of a database is just one thing, just that first thing I talked about, the database as a machine. This is the kind of database you're usually dealing with, right? There's something to get novelty into it. Maybe people are doing transactions against the database. And then if you wanted to do some sort of computation, issue a query or something like that, you're going to make up a request, which is something I want to have run, and you're going to have to pass it into the database process, and the database process is going to execute that in this black box context inside the middle of this moving machine and give you back some result. I think it's really critical to think about some of the issues associated with that. For instance, what's allowed in this function? Right? What are you allowed to do? Well, you're allowed to do whatever the database system says you can do in whatever language they support. Maybe it supports SQL, maybe it supports JavaScript, maybe it supports nothing. All you can do is do HTTP GETs or something like that. The other question is, can you get reproducible results? If I send the same request again later, will I get the same answer? Generally, in a system that has the database as a process and doesn't disentangle the state from the identity, the answer is no. You don't get the same answers over and over again. And the other tricky thing about the machine being the thing into which you send the computation is, how do you compose that? How do you make queries that manipulate more than one database at a time? Right? You have to because you're sending the request into a particular set of data. How do you make that request deal with this set of data? You make all these linking things or some nasty thing, or you have to copy the stuff out into another place, or you need to federate it or make some external thing to do that job. So we'll contrast that with the functional database process, where obviously this is still the same thing, right? It's accreting novelty. Different processes have said, oh, I learned about a new customer. Here's the new information. And then instead of doing anything else, the only other thing we get out of this is the ability to say, let me see your state. Let me see what the value of the database is. And so this machine will dispense values on demand. Here you go. Here's the value of the database. So the question here is, well, where's the computation? I showed you more stuff on the previous slide. Where is it here? And the answer is, it should not be here. This is a machine. This is a nasty, moving thing. Right? You play with machines, what happens? You get hurt. You stick your hand in a machine. It's bad. Right? Composing machines, it's difficult. So we want to separate computation from process. There is process, right? There is some state here. We're going to move on. We're going to put stuff on disks or in some sort of storage. But it doesn't mean we have to commingle that with computation. So we're going to have functional database computation is completely orthogonal to functional database processing. Right? Once we've got the values, we can write functions. Right? We can write a function. And the argument to the function is not some ambiguous, who knows what's inside the database while it's running. It's a clear thing. There's a database value. We're going to pass it to a function, and we're going to get a result out. The cool thing about having separated this is that there's no problem having a function that manipulates more than one database value. Right? It's just a function of two databases. And there's not a problem writing a function whose result is another database value. Right? So we have a function of two databases that produces a database. This is not a problem, because computation has been split out, presuming we can get something that looks like a value of the database. I've given other talks about how to do that architecturally, so for the purposes of this discussion, you're going to have to presume that that's possible, because it is. So there are a bunch of value propositions of values that we'd like to get from having done this. And what's the point? It's not just about to say, oh, I have a functional database, and where's my t-shirt? It's about getting some benefit. And we're looking for a lot of the benefits we get from using values in our programs. Right? The first thing is a database is just data. And data is language independent. Right? We're not talking about objects with methods written in a particular language with an interface or whatever. We're talking about information. Information doesn't have a programming language. Right? What's the programming language of information? There's no such thing. It doesn't even make sense. Right? It's just information, so it's just data. That's language independent. The other thing about data is that it composes and aggregates to data. When you combine two pieces of data, you get another piece of data. When you combine two machines, you get trouble. right? So that's a value proposition we're looking to get. There are other value propositions you get from using persistent data structures when you use a functional programming language. So a persistent data structure is a way to implement an immutable data structure, something big like a collection, such that you can give that collection to anybody, it will never change. But if somebody wants to make a modified view of that collection, they can, and it's inexpensive to do so. In particular, it's less expensive than copying the whole thing over. That's the benefit proposition of persistent data structures. That's what you get from functional programming languages. Most of the data structures are persistent data structures. And so what we want is the database to behave as if it was a persistent data structure. So in spite of the fact that there is, in fact, in the implementation I'm talking about, there is a persistent data structure in memory plus another persistent data structure in storage, and they get merged dynamically. I can treat that entire thing as a persistent data structure, and if I want to make a small incremental change that's local to me, I can do that and not impact anybody else because it's a persistent data structure and it's a value. And my changes aren't really changes. They're local trees with shared structure with the rest of the stuff. So some of the benefits we get from using persistent data structures are freedom from worrying when we alias, right? If you pass around copies of machines to people or pointers to machines to people, you have this immediate problem, right? Which is coordination of activity versus, with that thing, because it's moving around, people are issuing requests to it that cause it to move in different ways. Those requests can collide. It's almost impossible to obtain the state from the thing. So you worry a lot when you don't have immutable data structures about sharing them with anyone. It's like, well, the defensive copying, right? What a horrible term that is. Why do we do that? So when we use persistent data structures, we're free of that worry. Aliasing is cheap and completely free of worry because it is immutable. You can't interfere with each other. And we also want to get these benefits of efficient incremental change. So the other thing we get from functional programming is, we revisit that old Perlis quote, which is it's better to have one data structure and 100 functions that manipulate it than it is to have 10 data structures with 10 functions each. And that's super true. I think people are learning it in very tiny increments, but I believe that quite strongly. And so another benefit of having inverted this thing, instead of saying, here's my computation, it must comply with your rules, go let me do this, please. You turn it inside out and you say, give me your state. Then what can you do with that? You can do anything you want. Datomic happens to support data log queries, but you could write other query languages that manipulated the same data. You can directly access the indexes and write, kind of ordinary, functional mapping code across the data. You can get a view of the data if it happens to be hierarchical, as if it was a set of entities. By manipulating data and by walking through data structures, not by having to create and fabricate objects or do other kinds of ORM silliness, there is, in fact, information there. It is hierarchical. There are connections between the things, and you should be able to just navigate that all as data without any kind of additional stuff. So this is another expectation we get from having separated values and functions, right? We have a value, we can write a whole bunch of functions, right? A new function every day if you want that can manipulate this value, because the value is it's not opaque. It doesn't incorporate code. It's basically exposing itself, and it does so because it's immutable. So what can you possibly do in your function? You can't hurt it, right? So have at it. Write as many functions as you like. And that's the kind of approach we want to have. It should be an open thing. You have this information. Why should you be limited in how you consume it? Another really interesting property of persistent data structures and functional programming is that speculation is done completely differently than it is in an imperative context. Right? So if you want to have a what-if scenario and you have a whole bunch of data structures in an imperative, object-oriented program, and you wanted to say, what would it be like if I, moved everyone from here to there, or if I gave everybody a discount and then they told their mother about it, and then what would happen? And you just have to copy everything and go into this alternative universe. If that data happens to be in a database, there's almost no way to do it. Right? You can't put your speculative data in the database. Maybe you can try to abuse temp tables or something, but it's really not the same. But when we do functional programming and we try to write things that do speculative tree walking, right? We can just keep incrementing and incrementally enhancing our data structure. And if we get to a point in the tree where we say, this is a dead end, what does it take to backtrack? Well, you just drop that value. You don't have to undo it. You don't have to like fix your state or reset everything that you set along the path. You just drop it. So speculation ends up being a really important thing in functional programs. And when you can do speculative work with the database, it completely changes your life. So I'm going to show you in a minute a capability of Datomic, which is something called with, which takes a database value and some transaction data that you would normally send in a transaction and get a new database value, but you never did it. Like it's just a function of data, a database value and transaction data, and it gives you a new database value. But you don't have to send it over the connection and have everybody see it. And when you have that, it means you can do very, very interesting things. The simplest thing you can do is you can try before you buy, right? I want to do this transaction. Anybody ever seen somebody issue a transaction and then, wish they hadn't? Yeah, everybody's done that, right? Well, imagine if you could have tried that transaction first and seen how it worked out. In fact, and seen how your reports looked and seen everything about your system as if that had happened, but you didn't have to do it in a way that anybody else could see. It just really changes things. And then we've had people using the system to do that kind of tree propagation work where they had a very sophisticated change they wanted to do where it's hierarchical and there's some parent and you have to calculate something over the tree and calculate a new value of the parent and then recurse into each child. And they need to see the decision that was made by the parent and they sort of need to see a new view of the world. And you can actually flow the database through and have each branch incrementally enhance it and then issue queries against that what-if database to make their decisions about what to do and collect all the changes they intend to make back up when you return and say, okay, A, that all worked, and B, here's a set of things I need to transact against the database to bring it to that new state. Or you can discover something about it didn't work and make a different decision. Finally, again, this is not strictly a property of functional databases, but if you believe me that they must be accretive, that is, they must accumulate new information and not ever get rid of information, then you get a whole other bunch of great things that you're used to having, right? You all use Git. How many people use Git? How many people use a directory in their on their file server for source code? And you just like overwrite stuff? I mean, then we have, but who does it now? Yes, we don't do it anymore, right? Because we see so much of a value proposition in keeping what had happened before. So if you have an accretive value of a database, that means you have all the history in any particular value of the database, which means you can go and pretend it was an earlier time. Or you can see something that's happened in a particular time range. Or you can actually do queries that cross time, like how many times has somebody moved, or how many times have they changed their email address, or what's the frequency of change of our supplier's pricing to us, right? And all those kinds of things that you need to actually think about across time, right? If you only had the current value of everything, you really couldn't be very good at making decisions. And in all other cases, we don't accept that, but with databases we do for some reason. So we want to be able to do this. Finally, and everybody's always very interested in what the testing story is, well, it's phenomenally good. How many people like testing database code? Well, okay, so. The React guy likes testing database code. That's okay. I understand that. It's fun. Right. So how many people like code that flows connections around everywhere? Really a breeze, right? Because what's a connection? A connection is sort of like a pointer to a machine, right? And then how do you know what happens? I call this code, I flow a connection through, and it passes through. And we all know what the solution to this is, right? The solution is ambient connection pools. So we don't have to flow it. Right? Anybody who wants to at any point in time in our program can immediately say, give me a connection to whatever and let me go issue a query. And I'll get whatever's happening right then. Right? We know that's brutal, right? Because we have no idea what's happening. If 5 different points in the code go and make an independent call over that connection as part of subcomponents of a bigger computation, we have no idea that they all got things that make sense together. Right? There's no shared basis between that code. That's all independent. So it is like this big variable that we're passing around. So now we just completely switch from that. We once grab the value of the database and we pass it through our program. And then we know absolutely everything underneath is using the same value. And it means that we can write tests that are reproducible. Another phenomenal characteristic of values is that they're easy to fabricate. So if you have the database as a value, it means that mocking a database isn't making a connection that says yes to everything or pretends to do stuff, or having to reset a database from blank into some particular state. It means that you can just fabricate values in test code and send it to code that would otherwise expect a database, and that code will work. And the test code, the test values are things you can generate, make sure they exhaustively test ranges and things like that. So my intent with this talk was to give you a sense, was not to talk and talk and talk, which is what I usually do, about abstract things, but to give you a sense of what it's actually like to use something like this and touch it. So I'm going to, at tremendous risk to myself and especially to you, try to do something live. So that's not big enough, I'm presuming. Is it okay? Yeah. It's better if I can show you a little bit more. That way we won't be scrolling around too badly. So this is a brand new REPL I just called up, and this is Clojure code. If you don't know Clojure, don't worry about it. It just means exactly what it says, which is quite convenient. And there's no extra stuff. That's all you have to know. So we're going to load up some support code just to be able to talk to the database. And I should have put a note in here, which is, if I don't change this, you should all yell at me right now. But here I am changing it. So there's no need for yelling. So we're going to create a name for our database. There's actually a transactor running on this machine. And we're going to create a name, which is a URI for the database. And we're going to make one. And we're not going to make one because I don't know if I have this. Oh, I had to restart this. Hang on one second. There we go. You see, it's peril at every point. Every time I sleep my machine, I lose my connections. So there we go. And so what's happening here, oops, make this big again. What's happening here, just so people know, is this is the way you program, a way you program in Clojure, which is you leave your source code in one file, and there's a command I can hit on the keyboard. It's probably the only thing I know how to do in Emacs, that says evaluate the thing my cursor is on. So that's what I'm doing. So if you see my cursor up here, hey, true. That means we just created this database. Okay, and then we're going to get a connection to the database. So this is that critical thing. This connection, this is that machine. This is the machine side. When you're using databases traditionally, you're used to using the connection all the time. One of the things I want you to note in this part of the talk is how infrequently we do that. So we now have a connection to the database, and this means that anything we do via that connection is stuff that everybody else can see and can share. This is not really a tutorial, but there's a minimal schema required for Datomic. You basically define what attributes you're going to be able to put on entities. So we're just going to define one for this. This says that there is something, which is an attribute, which we're defining right here. That's name is email. Its value type is string. You can have one of them. It should be unique across the database. And the last attribute we're going to assert here is that that should become an attribute in the database. This object, this value is that. This thing I'm pointing at here is a representation of a Clojure map. So it's just key value, key value, key value. You can insert any Java map the same way. So have at it in your own programming language. And then we're going to actually transact across the connection. So we're going to transact across the connection, just sending that data. That's all we do. We send data in. Remember, that was that novelty. So there's some novelty. We're going to tell you about the email. We're going to do that right here. And that gives us back this thing, and def just says, call this name that value. So now we have schema ret, which is the return value from having transacted that schema data into the database. And that returns a map, and so we can look at the keys of that map, and we see some really interesting stuff right away. Transacting across the database returns the database before the transaction as a value, the database after the transaction as a value, any data created by the transaction, and a resolution of any temporary IDs that you created. That's pretty cool. So theoretically, the database after should be the value of the database having done that schema. We're going to call that new DB, just so that later we can talk about the database. This is the blank DB, new DB. And we can see, is the new database the same as the database before we transacted? We come down here and it says no. And now we're going to go and we're going to say this function, db, goes to the transaction and says, get me the latest database value. And because there's nobody else using this database right now, that should be the same thing as the after value, and it is. How many people have ever used equal on 2 database instances? Okay. So things are different already. And now we're going to define a little query. We're just going to keep reusing this query on different values of the database throughout the talk. So this says, find me some E and email where E has an email. Basically, this is get me all the emails. Give me the entity and the email, all of them in the database. And we're going to go and issue this query, and that's what Q is. We're going to say issue this query. So sending this value, this is again just a data structure. It's a Java util list. You could write it however you want in your own Java, JVM language. It's just a list. So we send that list, and we're going to pass the database value to query. Notice there's no connection in this call, right? There's not a query to a connection or to a server or anything else. It's a function of the database and the query value. And this is the empty set down here. We don't have any emails yet. We created the attribute. We haven't made any entities. So let's make one. We're going to transact again against the connection. This is the same kind of thing. I'll just put it in line. We'll say there's some new entity with the ID we're just making up, whose email is fred@email.com. And we're going to transact that. And just like before, that's the same kind of thing. It's a transaction that returns those same keys, right? The database before and after and whatnot. So it'd be interesting to recover Fred's identity because we're going to want to talk about Fred later. So the temp IDs part of that return value is a map. It's all the temporary IDs to the actual IDs you got in the database because the IDs are auto-generated. So this little piece of code just says, go into that return value, get the temp IDs, get the first one of them, and its value is Fred's ID. No fluff there. And if we look there, we see that's Fred's ID. We'll use that later. And that function was so interesting, we're going to name it NID because we can grab other IDs that way. Now, if we issue a query, because we just added Fred, whoa, got nothing. Why do we have nothing? Well, I didn't do anything. New DB. It's immutable. I hope I didn't mess that up. Somebody else could be using that, right? I didn't grab the new value of the database, right? I have the old value. So the DB after that was returned by the transaction is the value there. Now, what if other people are using this database? If I immediately went back and said, get me the database, could I get exactly the database that was produced by the Fred transaction? I don't know, maybe, maybe not, but I don't have to worry about that, right? It was returned to me from the transaction, so I'll just grab it. So the DB after I issue the Fred transaction is the one that includes Fred, I hope, and let's just see if that's the case. There he is. We have Fred in that value of the database. So now we're going to do a similar thing. Let's get this in view. We're going to add Ethel. Right, same exact thing. We're going to have some new temporary ID, and the email is Ethel, and we're going to put the return value of transact into Ethel DB. It has the same things, DB before, DB after, IDs, and whatever. We're going to name the value of the database that was created from that transaction, the Ethel DB. We didn't mess up Fred DB. Still has Fred in it. If we query the Ethel DB, we see we have both. And if we do actually go back over the connection again, because we're not sharing this database with anyone, we will see that the live database, I'll make this a little wider. The live database also has both Fred and Ethel. Are we okay so far? All right, let's start having fun. So let's say Fred wants to change his name to Freddie, and he's done it. He's told his mother, and she's still upset about it, but he's gotten his new email address, and that's it. Moving forward, but let's say this is the first time you ever use this database, and maybe you're not really sure that you know how to do this, right? So you're going to try it first. I have this transaction I want to issue to make Fred's name Freddie, and I'm going to write that as data here, and I'm just going to name that. So I have a value called FreddyTX, and it really is just that. Anytime I type down here, you should tell me don't do that because you're just going to mess up and use code you didn't try before. No, there it is. Okay, so this just says we're going to make a guy. We're going to make Freddie here. Then we're going to do something completely different, right? We're not going to call transact. This arrow thing just says take the first thing and pass it to the next thing and pass it to the next thing. It's a way so that I can write code in order that you're probably more familiar with. So we're going to take the value of the database from the connection. And we're going to get a value of the database. We saw this before. We get a value from doing this. They want to say, imagine that database, or give me a new database as if I had done this Freddie transaction to it, the one I just wrote up here. And that returns the same stuff that transact does. So I'm going to get the DB after it. I'll call that Freddie DB to see what happened. And what's going to happen when I look at Freddie DB? Will Fred become Freddie? No, actually, I made a mistake. What was my mistake? Yeah, I actually just made a new guy. I didn't talk about Fred. I just said there's somebody else who has a Freddie. But thank goodness I didn't really do this, right? If I go and look at the connection, look at the database that everyone's seeing, I didn't talk to the connection, to do this job. Therefore, I didn't change anything. So let me see if I can fix that. Right? What I want to do is say, Fred's new email is this. I'm just adding a new fact. I'm not doing anything else. And I'm going to name that thing, and I'm going to try that again the same way. Take the fresh value of the database, imagine it with Fred transaction, and see what happens. And we'll lose that, and now we'll issue the query here. And that's what I expected to see. This same ID, 418, that was Fred, is now Freddie. That's good. Fred changed his name and changed his email. So now we'll do this for real, right? We're going to take that same transaction data and instead send it to the connection using transact like we did before. We're saying now, okay, apply this change to the value of the database that other people might see. This is just chaining it. Take the connection, pass that transaction to it, dereference it, and grab the database after. So that's the new Freddie DB. And we issue the query, we see that. But now if we look at the database that everyone sees Freddie. Everybody good? Okay, so now we're going to look at that accretive nature, which is that every value of a database contains all prior values of the database. So we're just going to get the latest value of the database, and we're going to call it latest DB. Okay, so we ask the connection to get the value, and we now have the value. We're done with the connection. And we'll just issue our same query again to make sure what our basis is. This is the current view of the world, Freddie and Ethel. But now we have this new function here called history. And history takes a database and says, instead of just showing me the current truth, the most recent true value of every attribute that you know, show me every value of the attributes that you ever knew. How many people would like to be able to do that sometimes? Yeah, I did. So there we go. So this is very interesting. So now we see, unlike in all the other queries, that 418 can come up more than once. We have Freddie here and we have Fred there. Now this is kind of neat, except I don't know if I could make any decisions on this basis. Why not? I don't know when. Boy, I wish I had a database that remembered when things happened. And it ends up that you do, right? So what I've been showing you is a query that binds only 3 of what are actually 5 parts of what we call a datum, right? Which is a fact. The first is what entity, the second is what attribute, and then the value. But the fourth thing is when. What transaction was this true? So I'm now just going to enhance the query, and we'll call it T-query, which will pull back that additional thing. So we'll get the ID, the value, and the transaction. And when I issue this, I get back the transaction times. But what else is really interesting? How many results did I get last time when I used history? 3. How many did I get now? 4. And what's interesting about those 4 is that the 2 of them have time 317 at the end here. One says Freddie and one says Fred. So I'm still not really able to distinguish these because these 2 things happened at the same time. What's different about them, do you think? Right. One was, I'm saying this is true, and the other one is saying, I'm saying this is no longer true. Right? One was an assertion and one was a retraction. And it ends up that 5th part of a datum tells you that. So if you are looking at history, you're probably interested not only in the time, but also whether or not things were asserted or retracted. So the full kahuna can grab the entity, the attribute, the value, the time, and whether it was an assertion or retraction. So that's full query, and if we issue full query, we see that we were asserting Freddie at 317, but we were retracting Fred at that point in time. That seems like something you could do reasonably cool analytics with, I think. So the other thing that's useful about having all of history inside something is if there was a way to say, I found this cool thing back then, or I just did something at this point in time, I'd like to tell you about it. Maybe I'm going to send you an email. But I know the database is going to keep moving along. The process, the business is active and things are happening. I wish there was a way for you to get back to the thing that I saw, or for me to get back to the thing I saw. And that's about having a basis that you can recover and look at and send around. So wouldn't that be nice if we could get that? And we're going to go back now, and remember we captured FredDB right after we added Fred. And it ends up that we can ask any database for its basis T, which is the time, there's a monotonic time that increases in the database that labels every point. So we'll say, what was the point in that database? And we'll see that's 1001. And it ends up that T's have a relationship to TX's. So we saw TX's earlier, and you can translate from one to the other. A TX is actually an entity, because transactions are entities, but the T is inside their transaction ID, so we can turn one into the other. So this is 313, and that's what we have up here, right? This assertion of Fred came in transaction 313, and 1001 and 313 are the same things. It's just we don't want to have to send those giant numbers around and have people try to understand them. So now we have this basis, and we called it Fred T. So now we have two other really cool things we can do. We can say, this is the latest database, but I'd love to see it as it was at time 1001. And I'm going to go and get that value and pass it to query. Now you'll notice I'm not changing query. Same query, different value of the database. And if I issue that query, boom, it's as if I never saw Ethel or Fred never changed his name. The other thing I can do is I can say, let me see the database, only the stuff that's happened since that, in other words, after that. And if I issue that query, I'll see Freddie and Ethel. So I can see the database before, since, or combinations of that give you windows of time. And finally, we can talk about seeing more than one database. So this is a slightly more involved query, and we add this in clause, which says I'm going to give you data sources. If you don't supply the in clause, query presumes you're going to give it one argument, which is the data source implied for all of it. If you're going to have more than one data source, you have to name them in, and you have to name them in these binding clauses. So we're going to name two data sources, D1 and D2, and we now expand, so the actual binding form is database entity attribute value time assertion. And this basically says, show me everybody that was the same in both databases, had the same email in both databases. So what should we get? If we issue this query against the Ethel database, which has what in it? Fred and Ethel. And the latest database, which has what in it? Ethel and Freddie. What should we get? Ethel. Oh, we should make this exist. There we go. We get Ethel. So there we go. We can imagine sending other databases and doing interesting things between databases, but the principle I showed in that picture applies. So we were talking about testing. I wonder what I would do if I wanted to test this. Should I create two databases and fill them up with stuff? It's like, that's so hard, right? Even with this, it's hard. Why should I have to do that? That's all this, like, I have to set up machines to run. I wish I could just supply data in the same shape that the database values are and have queries work against that. So here's that same query. Here's two relations written as lists of lists. And when the query is, what's the same in both databases? Same query. Query against databases. We just saw it work against databases. That database could have the entirety of, giant thing on DynamoDB behind it. We could test it with two lists. Obviously, we know how to make lists. So, okay, we're going to switch gears now, and I just want to show you the paradigm shift. So I'm going to actually connect to a database that's already installed, which is a large music database derived from the MusicBrainz data. and get a connection to it and get a value of the database from that connection. I'm going to call it DB. So I have a second database, another connection. I grab the database value from that. There's no problem doing this. And if I had any relationship between these two databases, I could supply the music database and the email database, but I don't. OK, so I'm going to go a little bit more quickly through this. This is a query that says, find me the artist whose name is the Foo Fighters. And it's just going to go and grab the first return value because there'll be only one, and that's the Foo Fighters ID. So we do that, and we look at FFID, and we see it's some number. We don't really care. But now there's another completely different way of looking at the same data value, right? The same value of the database, which is more entity-oriented. That's not to say it's object-oriented and the objects aren't created. It's as if there was a big map and it could point to other things, and each of the attributes points to other things. It's implicit in the data, right? The data has hierarchical structure implicitly. Albums have artists and things like that. So I'm going to make an entity, which is sort of a lazy way, a lazy map, from the value of the database. So we're done with the connection, not using the connection. From the value of the database, the value of the music database, which is huge. It has 100 millions of stuff in it, hundreds of millions of facts. I'm going to give me the entity corresponding to the Foo Fighters. And then it behaves like a map, so I can ask for its keys. And so the Foo Fighters is an artist, so they have a start year and country and some other stuff. So we can see what year did the Foo Fighters start. Now, I'm not in a query language here. I'm using Clojure's facilities for manipulating maps. But if you want to use Java's facilities for manipulating maps, it would work just the same way. It's not different. You call get and stuff like that. So that's kind of cool, but it ends up that artists aren't that interesting. They have facts about themselves. I know the database knows which albums are by the Foo Fighters, but that actually is a property of the album. So albums have artists instead of artists have albums, and there's always that kind of choice. Which should it be? If I get that wrong, will I be screwed and not be able to find my stuff? It ends up no, right? First of all, it is correct to say that artists have albums because there might be more than one artist on an album. But since I've organized it that way, what if I wanted to find what albums were by the Foo Fighters? Do I need to go back to query and things like that? It ends up that no. It ends up that I happen to know that that there is this attribute called release artist, which is what are the artists on a release, who made this album. And if you use this little underscore, it means you can go backwards. So this basically says, show me all the releases that have the Foo Fighters as an artist. And this is not a query. This is just, you're using this it's like a field lookup. It's imagining the Foo Fighters had this attribute, which was who points to you. It's fixing objects, right? Objects pointers only go one way. Here, it's relational. Pointers go both ways. In fact, they're not really pointers. They're more like bridges. And there we go. These are all the releases. So that's not that interesting because these are just the IDs. But you'll notice these are like little maps. In fact, they're lazy entities just like the one we just saw. One for every release that has the Foo Fighters. So if I take that, that set and grab the first one and look at the keys, I now can see these are the keys of a release. Right? These are the attributes a release has. And so finally I can go and just use regular functional programming to take the Foo Fighters, grab the releases that have the Foo Fighters as an artist, map this higher order function that says grab these three attributes and put them next to each other in a tuple, and then print them. There's no query language here. This is regular functional programming. And we do that, and we get that. So with that, we'll go back. So I think that when you finally have this, having a functional approach to a database brings the same kind of benefits you get from using functional programming otherwise. And there are many, and they're extremely valuable. You also get a lot of new stuff. There's several things here that I think are extremely difficult, if not impossible, to do otherwise. And the most important thing, and the real reason to be here, and to pursue this, is that this makes programming, and programming that involves databases, much simpler in the core way, in the core meaning of simple, much less entangled than it has ever been, and that's really the point. So thanks very much.